Hello students, our today's topic is rotational vibrational Raman spectroscopy. In order to understand that, firstly we will consider the rotational Raman spectroscopy. What is it? It is similar to the rotational spectroscopy. It means there is a transition between the rotational energy levels. In this case, in the case of the Raman spectroscopy, if we consider the rotational Raman spectra, then here the selection rule is del J is equal to 0 or plus minus 2. Here J is the rotational quantum number. When the del J is equal to 0, it means there will be no change in the frequency of the scattered radiation as compared to the incident radiation. It means the frequency is same. So we will observe the Rayleigh scattering. And here of our interest, the selection rule is del J is equal to plus or minus 2. That is about the Raman scattering. It is considered with the Raman scattering because in this case there is a change in the frequency of the scattered radiation. And when we consider del J is equal to plus 2, when del J value is equal to plus 2, then we consider the absorption. It means the molecule will go to the higher, the excited to the higher energy level. So the frequency of the scattered radiation will be lower as compared to that of the incident radiation. And when we consider del J is equal to minus 2, then it will be for the anti-Stokes line. It means the molecule is deactivated to the ground state and there is the frequency change. It means the frequency of the scattered radiation will be higher as compared to that of the incident radiation. The rotational term is given by Fj is equal to B bar J plus 1 centimeter minus 1. It means this is in the wave number and here B is the rotational constant and this J is the rotational quantum number. Its value may be 0, 1, 2 and so on. So for a transition that takes place from any level J to the J plus 2. It means when we are considering the selection rule del J is equal to plus 2 and the transition takes place from any level J to J plus 2, then the frequency of the transition will be given by del Fj is equal to Fj plus 2 minus Fj. It means we will subtract it from this and we can put its value. So B bar J plus 2 times J plus 2 minus B bar J plus 1. So we will get the value is equal to B bar times 4J plus 6, or we can say 2B bar times 2J plus 3 centimeter minus 1. So this will be the frequency of the transition. As we know that the frequency of the Stokes scattered lines is always lower as compared to the frequency of the incident radiation. So in order to find out the frequency of the Stokes lines, what we will do, this is the energy separation. So we will subtract this value from the frequency of the incident radiation or the frequency of the exciting radiation. So the frequency of the Stokes line will be given by nu bar S will be equal to nu bar of the exciting radiation minus 2B bar times 2J plus 3 centimeter minus 1, because this is the frequency difference and we will subtract it. So we will get a frequency of the Stokes line. Now the displacement of these Stokes lines from the incident radiations are 6B bar, 10B bar, 14B bar and so on in the wave number terms. It means the first line, the frequency separation of the first line from the incident radiation will be 6 bar centimeter minus 1. That of the second line will be 10 B bar centimeter minus 1. That of the third line will be 14 B bar centimeter minus 1 and so on. Similarly, the frequency of the anti-Stokes line will be obtained by the addition of this term to the frequency of the exciting radiation. Why? Because we know that the frequency of the anti-Stokes line is always higher as compared to that of the incident radiation. So the frequency of the anti-stock line will be equal to nu bar of the excitation plus 2b bar times 2j plus 3 centimeter minus 1. And in this case also the displacement will be same. It means the first line will have a separation of 6b bar, the second line will have a separation of 10b bar, and the third line will have a separation of 14b bar centimeter minus 1. So if we see the rotational transitions in the Raman spectra, it will look like this. These are the different rotational energy levels and their values are J is equal to 0, 1, 2, 3, 4 and 5. And with increasing the levels, the energy gap between them is increasing. You can see that this energy gap is small and it is increasing constantly. So we can see that we know that the selection rule for the rotational spectroscopy is del J should be equal to plus or minus 2. So when the value of del J is equal to plus 2, it means the transition can happen from J is equal to 0 to J is equal to 2, from J is equal to 1 to J is equal to 3, from J is equal to 2 to J is equal to 4, or can be happen from J is equal to, this will be J is equal to 3 to J is equal to 5. It means the difference between two successive levels, it should be equal to plus 2, so that we will get the Stokes line. Similarly, when the value of del J is equal to minus 2, this will be del J. This is the del J. So when the value of del J is equal to minus 2, the transitions will be opposite. It means the transition may be from J is equal to 5 to J is equal to 3, J is equal to 4 to J is equal to 2, J is equal to 3 to J is equal to 1, or from J is equal to 2 to J is equal to 0. So this will give rise to the anti-Stokes line. So if we see the rotational Raman spectrum, it will look like this. It will have a series of lines equally separated from the incident radiation. It means Rayleigh line. This middle line is the frequency of the exciting radiation and it is called the Rayleigh line. When the value of del J is equal to 0, then we will get this type of line. It means when the frequency of the scattered radiation is similar to that of the exciting radiation. So we will get a line in the middle and the intensity of this line will be very high because most of our scattering is in the form of the Rayleigh scattering. Now in this side we get the Stokes line. It means the frequency of these lines is lower as compared to that of the incident line. So these are the Stokes line and their separation is, the separation of the first line from the middle is 6b centimeter minus 1, while that of the other lines is 4b and all are equally spaced. And in this side these are the anti-Stokes lines. It means the frequency of these lines will be the frequency of the scattered radiation through the anti-Stokes will be higher as compared to that of the incident radiation. So we get these lines. Now you can see that this first line is separated by 6b centimeter minus 1, while the other lines are separated equally by 4b centimeter minus 1. If we see their intensity, then the intensity firstly increases to a sudden value, to a value, definite value of the J, that will be called the J max, and at this value it approaches to a maximum and then it decreases and we get the decreased intensities line. So at a fixed point of the J value, the intensity is the maximum, that is called the J max. Now we consider the vibrational Raman spectroscopy. When we consider the pure vibrational Raman spectra, the energy term in the wave number is given by V plus half omega E bar minus V plus half square omega E bar Xe. Here Xe is the anharmonicity constant and we are considering this term for the anharmonic oscillators. So the selection rule for the pure vibrational Raman spectra is del V is equal to 0, plus minus 1, plus minus 2, plus minus 3 and so on. And the frequency of the transition between two levels is given by del nu is equal to omega E times 1 minus 2xe centimeter minus 1. So the frequency of the Stokes line will be obtained by subtracting this value from the frequency of the incident radiation. It means the frequency of the Stokes line will be equal to nu of the excitation minus omega E bar times 1 minus 2xe. Similarly, the frequency of the anti-Stokes line will be obtained by adding this value in the frequency of the incident radiation, because the frequency of the anti-Stokes lines is higher than that of the incident light. So the frequency of the anti-Stokes line will be nu excitation plus omega E bar times 1 plus 2xe. Now we consider the vibrational rotational Raman spectroscopy. In actual, we does not observe the pure vibrational Raman spectras. Why? Because the energy of the rotational transition is very small. These are the rotational levels and the energy gap between them is very small. These are observed in the microwave region. It means the absorption of the microwave radiations will cause a transition between the rotational levels. The energy of it is very small as compared to that of the vibrational transitions. If we consider the gap between two vibrational levels, it will be very large. This is generally observed in the IR region. So these are two vibrational levels. We have made them by the dark lines. These are two vibrational levels, and we can see that the gap between them is very large, and in between these two vibrational levels there are several closely spaced. These are the rotational energy levels. These are present between the two successive vibrational levels. So when we cause a transition between the vibrational levels, if we cause a transition between them by the absorption of IR radiations, then there will be a simultaneous transitions between these levels. There will be transition between these levels. So the vibrational transitions are always accompanied with the rotational transitions. So in general, that we observe is the vibrational rotational spectras. So here we will concern the vibrational rotational Raman spectras. The selection rule for the vibrational rotational Raman spectra of the diatomic molecule is del V is equal to 0 or plus minus 1 and del J is equal to 0 or plus minus 2. In actual, at the room temperature, most of the molecules are in the ground vibrational state. It means the V value is equal to 0. So the most important transition that we consider is from the V is equal to 0 to V is equal to 1, and it is of our interest. So there are 4 different possibilities, and we will get 4 different types of line. When del V is equal to 0 and del J is equal to 0, it means there is no change in the frequency of the scattered radiation, and we will get the Rayleigh lines. When del V is equal to plus or minus 1 and del J is equal to 0, it means there is no rotational transition. The rotational levels are same in both the vibrational state. So we are getting the pure vibrational spectra, and it we will call the Q branch. We will obtain it in the middle of the spectra. Another condition is when del V is equal to plus or minus 1 and del J is equal to plus 2, then we will get the S branch. And when del V is equal to plus or minus 1 and del J is equal to minus 2, then we will observe the O branch of the vibrational rotational Raman spectra. So in the vibrational rotational Raman spectra, we observe 3 different lines. In the middle we will get the Q branch that are closely spaced, and in general we observe a single line in that case. And in both the sides we will observe the S branch and the O branch. The vibrational rotational Raman transitions will look like this. These are the 2 vibrational levels, that is V is equal to 0 and this is V is equal to 1. and in each of the vibrational levels there are several closely spaced rotational energy levels. In this case also and in this case also there are several closely spaced rotational energy levels, and their values are J is equal to 0, 1, 2, 3, 4, 5, 6. These are the different rotational quantum numbers of different rotational levels. Now the transitions that can take place in the middle, we will observe the transitions for del J is equal to 0. It means when there is no change in the rotational quantum number, a transition takes place from J is equal to 0 to J is equal to 0 of the higher vibrational level, from J is equal to 1 to J is equal to 1. Similarly, different transitions are taking place between the same rotational quantum numbers. So we observe a set of closely spaced lines in the middle of the spectra that are called the Q branch. Similarly, when we see the value of del J is equal to plus 2, then we observe S branch of the lines. This is a transition from J is equal to 0 to J is equal to plus 2, J is equal to 1 to J is equal to plus 3, and similarly different transitions are taking place in which the value of the quantum number is increasing by plus 2. The molecule, the excitation is taking place from a rotational level to the another rotational level of the another vibrational state, that is increasing by plus 2. So we observe the S branch. Another branch is the O branch, that is observed when the del J value is equal to minus 2. It means here the rotational level is higher. The rotational quantum number is here higher by 2, and here it is lower. It means a molecule is exciting from the higher rotational level of the ground vibrational state to the lower rotational level of the higher vibrational state. It means the transition is taking place from J is equal to 2 to the J is equal to 0, J is equal to 3 to J is equal to 1, J is equal to 4 to J is equal to 2. In this way the different transitions are taking place, and in this way we get the O branch of the spectroscopy. So in the middle we get the Q branch, and in this side we are getting S branch, and in this side we are getting the O branch of the Raman spectroscopy. So the vibrational rotational Raman spectra will look like this. In the middle we will get a highly intense line, that is the Q branch, and that is the when the value of del J is equal to 0, and at the both sides we get the equally spaced lines. These lines are for the S branch and these lines are for the O branch when the del J value is equal to minus 2 and when the del J value is equal to plus 2. So this is all about the Raman spectroscopy. In our previous videos we have studied about its principle, and in this video we have studied about the rotational and the vibrational spectroscopy. Hope you will like this video. Thank you.